All right, let's continue our journey in soil fertility, focusing on Unit 3, where we're going to touch on soil acidity and alkalinity. And there's 9 objectives. This is a relatively big unit because pH or acidity and alkalinity play a major role in nutrient availability, either directly or indirectly. And so you see 9 objectives. You should be able to, at the end of this unit, describe the effects of low and high pH on plant nutrient availability. Should be able to tell me and others natural and anthropogenic sources of soil acidity. You should be able to describe and quantify active versus potential acidity. Then describe common methods to quantify lime requirements in soils in order to raise soil pH. Identify liming materials and quantify their relative effectiveness in neutralizing soil acidity to improve crop growth. This is why we do this. Should be able to calculate a lime application rate or rates given a liming recommendation. Objective number 7, discuss both direct and indirect benefits of liming acid soils and the factors that determine a good liming program. Objective number 8 is to discuss the conditions where acidifying high pH soils will be necessary and practical and suggest appropriate sources of acidifying materials. And that'll be an interesting objective when we get to it. And the last objective for this unit is to know the rule of thumb for sulfur application rates to remove excess lime from a soil and thus lower the pH. So this unit focuses either directly or indirectly on soil pH. And so what is pH? You've all learned about pH somewhere along the line in your career. pH is simply the negative log of the hydrogen ion concentration. That's what it's expressed here, right? It's on a log scale, and this will make sense in a minute. Another way to express it is pH is the log of 1 over the hydrogen ion concentration. Both of these equations equal one another. So you can imagine if we use this second equation here, and when the hydrogen ion concentration goes up in a soil, this denominator becomes larger, and it's 1 divided by a relatively large number, which makes pH smaller, or goes down. And this is how the pH scale works. And it's all described on a log scale, log to the base 10. So here's a relationship of pH and basically acidity. We won't get into the details of everything on this slide, but let's look at pH, this first column on the left, and the acidity, or another way of looking at this is the amount of hydrogen ions present. Okay. And so you can see that these numbers in the second column get smaller and smaller and smaller by an order of tenfold as you go down the pH scale. Okay. Or if you go up the pH scale, the amount of hydrogen ions increases tenfold for every 1 unit pH increase. And they decrease, the amount of hydrogen ions that are present decrease tenfold for every pH unit increase. And thus, this is why when we describe pH, instead of describing it based on the concentration of hydrogens, we describe it on a log of the negative log of the pH, or negative log of the hydrogen ion concentration. Okay, because it's simpler for me to tell you that pH of my solution is 14, instead of me saying it's the amount of hydrogens present is 0.00000000000001. Nobody is going to do that. So we use the pH scale to represent these values that you see in the second column. Now, you probably learned that pH goes from 0 to 14, and whatever you learn would be incorrect. pH can actually go slightly lower than 0, and it can be slightly greater than 14. pH of concentrated hydrochloric acid is negative, I can't remember, it's negative 0.6 or negative 0.4, but it's below 0. And concentrated sodium hydroxide probably has a pH of slightly above 14. But in general, this is the pH scale from 0 to 14. And there's a sweet spot or zone in which plants like to thrive. And you'll see that in this video. The other thing I want to point your attention to is, well, misspelling, a more detailed table of this can be found in Carmen Canvas under Unit 3 Notes and PowerPoint Slides in that section in Carmen Canvas under Modules. And it's a table that describes a number of different crops, more so than what you see here. The list is actually, it should be 2 to 3 pages long. It's 4 pages long that shows you or represents the range of pH values that these particular crops like to grow within. And I just present it to you for your own information. And I want you to know that it is posted online, just in case you want to look at it. I'm not going to test you on it. So let me give you an introduction to this unit. Soil pH. If I had to measure one constituent, I couldn't do it anymore because I've studied soils for too long. When I was younger, if I had to measure one constituent in a soil, it would be pH. Why? Because pH directly or indirectly affects nutrient availability across a wide swath of nutrients. Okay? It affects nitrogen basically indirectly because of the release of nitrogen from organic forms of nitrogen by microorganisms that like a certain range of pH values. It certainly and directly affects calcium, zinc, copper release and availability in soils, certainly magnesium, manganese, aluminum, molybdenum, iron, potassium and phosphorus and others. And so this is the importance of knowing what the soil pH is. If you know the soil pH and you know what plant you want to grow, you can basically adjust the pH. It's easier to adjust it upward from acidic to neutral or basic than going the other way around, but you can adjust the pH to meet where the crop falls on the pH scale on that table that is in Carmen Canvas. And so here's an example. This is an example picture of corn growing in an acidic soil. I don't know where this picture was taken, but on the left, there was no lime. And on the right, there were 3 tons per acre of lime added. The pH was raised on the right to increase nutrient availability and subsequently promote better crop growth versus the soil on the left with no lime. The plants on the left are likely suffering from either a deficiency or a toxicity due to potentially aluminum or free hydrogen ions. The plants on the right are not suffering at all. And this is directly related to pH. This is why pH is really important to understand and why we have a whole unit dedicated to this subject. So the general influence of pH on crop growth goes like this. When we have pH values less than about 5.5, we sometimes or oftentimes, depending on the crop, see aluminum or manganese toxicity. And in terms of what occurs within the plant, aluminum and or manganese concentrations in the soil can be great enough where when the apical meristem is growing through the soil, it will touch excess aluminum or manganese, and excess manganese or aluminum kills the apical meristem. And eventually what you see are either shortened, stunted roots that look dark brown in color. They sometimes are called a club foot or club root. And subsequently, you notice that the above ground growth suffers because of the toxicity. Another general influence of pH is that micronutrient concentrations and heavy metal concentrations tend to become toxic at pH values less than 5. And for the micronutrients, this is true for zinc and copper. but that also holds true for other heavy metals like lead and cadmium, etc., below about pH 5. Point number 3 is that calcium, magnesium, and molybdenum deficiencies can occur at low pH values. And micronutrients tend to become deficient, specifically zinc and iron, but manganese and copper, they become deficient at high pH values, above 7.5 to maybe 8 or greater. And then you have phosphorus, and phosphorus can be deficient at both low pH values and at high pH values, because as you learned in Unit 2, I mentioned briefly that phosphorus loves to be loved. It loves to be bound at low pH values to iron and aluminum mineral phases, and it loves to be bound to calcium mineral phases at high pH values. So let me show you some examples. Here's an example of normal soybean on the left and zinc toxicity on the right. And when you see this, this leaf doesn't really look like a deficiency. That you'll learn this throughout this semester. This definitely is not a deficiency symptom. If you were to remove the roots from the soil, you would see this. You would see the normal roots that look relatively thick, and you would see a club root where the apical meristem has been killed and the root is struggling to throw out lateral roots and root hairs because the lateral root hair, or I'm sorry, the lateral roots apical meristem is being killed by zinc in the soil. And this is due to low pH, typically below 5. Here are some pictures of iron deficiency in strawberry on the left and a maple tree on the right. And this is classic iron deficiency, at least in the maple tree, where you see interveinal chlorosis. By that, I mean in between the veins is chlorotic or yellow, and the veins are not. This occurs at high pH, typically above 7.5 to 8. So pH indirectly affects other crop growth requirements. For example, low pH is going to certainly restricts root growth. And because root growth is limited, you have limited uptake of water and you have limited uptake of nutrients. So for example, in this picture on the right-hand side is cotton growing at pH 6.5, and the main root is going rather deep into the soil profile, while at pH 5.2 and 5.5, the roots are stunted, they're certainly shorter, and they actually look a little browner in some locations as compared to, quote, normal roots. And that's because at these low pH values, aluminum is likely toxic and killing the apical meristem of the root itself. And you get this club root, and the root system simply cannot explore the soil enough to find water and nutrients. So hopefully you've seen a figure much like this on this screen, and I really like this figure. And what this figure shows you are basically the essential nutrients for plant growth in all these bars as a function of pH. And you can describe pH as strongly acidic to strongly alkaline, or you can use the pH scale. The green on the bars means good, the yellow means cautious, and the red means bad. It's like a stoplight. And where you see green is where the greatest amount or availability of each nutrient is located on the pH scale. So for example, nitrogen tends to be most available between 6 and not quite 8, all right, 7.7. And this is driven by microorganisms primarily. Phosphorus tends to be most available between about 6.5 to maybe just a hair below 7. And that's because below this value of 6.5, phosphorus loves to be loved via formation of aluminum and iron mineral precipitates. So iron phosphates, aluminum phosphate mineral phases. And above about 7.5, phosphorus loves to form associations with calcium to form calcium phosphates. And those are insoluble minerals. So there's a sweet spot for phosphorus. There's certainly a sweet spot for potassium. It's rather large, same with sulfur. A narrow window for calcium, not so much for magnesium. And then when you see some of these micronutrients. The micronutrients, by and large, tend to be most available at rather low pH values, and their availability decreases as pH increases. And we typically see deficiency symptoms in the micronutrients at around pH 8 or so. And molybdenum is a little bit opposite, where you see sufficiency at high pH and deficiency at low pH. Now, if you look at this figure as a whole, it's telling you a story that there's sort of a sweet spot somewhere in here. Oops, sorry about that. There's a sweet spot somewhere, maybe very slightly acidic to neutral, roughly speaking, where most of these nutrients are maximized in terms of availability. And that's true. And so our plants that we grow bracket this sweet spot. And in fact, if you went back to that table with 4 pages that bracket the types of plants that we grow, you'll notice that they typically range between probably about 5.5 to 8, because plants like to grow within these regions, and so do microorganisms. So I'm not going to test you on this subject yet, but when we get to these individual units, we'll talk about this in more detail.